Okay, so I'd like to thank everybody for being here. Sorry I'm not there in person. I got a little sick, and so I'm sort of recovering. So if anything seems a little off, just blame it on that. But if you do have questions, please ask questions. So I want to talk a little bit about physical maze solvers, modern portfolio theory, and some vague relation there. But also, this is really a talk about eventually this will turn into a talk about how great reproducing kernel Hilbert spaces are. And it's also meant to be an invitation to that theory, which is very nice because it allows you to take your data and then turn it into something with Hilbert space geometry or something like that via these kernel embeddings. But also kernels have their own sort of function theoretic life, and we sort of want to talk about that a little bit. So first, I want to talk a little bit about mazes. So, for example, here we could have a maze. There's an orange dot. The orange dot wants to escape from the maze. That's great. Okay, so we could do something. So we could ask the question, okay, we could grid this maze out like this. So we've seen this happen a few times where we sort of grid out the maze. And so we have our orange circle is trying to get to these green goals, which is the outside of the maze, something like that. And this is some way of parametrizing like the open space in the maze. Okay, so on the other hand, though, the maze is the thing that we would bump into if we were trying to get out of it. So sort of worrying just about the inside of the maze, is this really the same object? That's sort of not so important, but the point is that, okay, so we could discretize our maze now and we can forget about the walls. Okay. But there are maze solvers, especially physical maze solvers, that really use the walls in some way. So, for example, imagine there's this stinky piece of cheese put outside of the maze. It's a hot day. So then smell lines start coming out of the cheese, and this little orange minotaur can then follow his nose to get out of the maze. Okay, something like that. And so sort of the main thing that this uses is the fact that, Avogadro's number is big, that the chemicals sort of can almost continuously diffuse, and that sort of you're doing something massively in parallel there, which is just sort of interesting. So now I want to talk a little bit about sort of a game that's rigged in your favor. So let's say that I have a game where whenever I flip a coin, on heads, you get double your bet, and on tails, you get 2/5 your bet. So if I go in every day, am I going to win? So the point is that, okay, so let's say that I have $10. Today I make the bet and I win. Then I have $20. And then I could play again, maybe the next day, and then I would, with all my $20, and let's say that I lose, then I would only have $8 left over. So okay. The median outcome after n flips is actually 2 times 2/5 to the n, which goes to 0 as n goes to infinity. So even though the expectation of this game, okay, if I take the average of 2 and 2/5, I think I get 6/5. Even though the expectation is above 1, I'm still going to lose if I go all in constantly. And you might ask if certain kinds of securities behave this way. Certainly, this sort of fits with the idea of something like a growth stock, something with very, very high risk. But there's something interesting here. So if we play twice and we split our money, so let's say I have $10, I bet $5 on one coin flip and $5 on another coin flip each day. So I split my money into two, essentially, the same game. And the median outcome here is going to be something that's a little bit above 1 to the n, which is going to go to, sorry, that should say goes to infinity as n goes to infinity. So this is good. Sorry, this is a typo here. Okay, so this says that if we sort of diversify into two different coins, we can actually make the game work in our favor, even though if we were to only do it with one coin, it would we would get zeros and goes to infinity. This again should be an infinity here. Okay, so diversification is well captured by something that's known as the arithmetic geometric mean inequality. So if I have a sequence of positive numbers and I take their average, that's always going to be bigger than their geometric average. And so this says that doing things in parallel, or making bets in parallel, which is sort of the arithmetic side, is going to beat making bids in sequence. So that's sort of, this sort of fundamentally captures a lot of what diversification is about. Okay. So there's this notion from Adam Smith about the invisible hand. So we have things like securities that could have, again, very perverse behavior. And yet somehow we end up with some supposed positive structure. So, it's not totally clear if that's really true, but I mean, we see a lot of things like economics incentivizing poor behavior, like things related to climate change, human rights, etc. But the point is that, what Adam Smith was talking about was he was talking about how even though there might be incentives, say, for all business to move offshore, for some reason, some of it was staying in the UK. And there's various sorts of things that people have seen other than just the invisible hand in the market, things that people sort of feel like have agency. For example, people see animal spirits, the bear and the bull inside of the market. And there's also things related to ideas of value versus growth. So, for example, if I have some company that's well managed, that's not taking super high risks, somehow that's fundamentally different than, and certainly is interested in paying a dividend, that's fundamentally different from things that are making just huge gambles like what we saw before. Although they may still go to zero by themselves. Okay, and so the other thing that I want to talk about is there's notions like the efficient market hypothesis, which sort of also captures some basic ideas about investment. So, for example, that somehow the prices should be correct and that the existence of the market as it exists should be correct. So what that means is that if I wanted to optimize a portfolio, what should I do? I should positively buy everything in accordance to which it exists. So if if Apple is twice as big as, Tesla or something, I would want to buy twice as much Apple as Tesla or something, regardless of what the companies are doing, something like that. And there's some sense, in markets somehow, whenever we talk about their perverse behavior, we could see this even after, so joint stock companies were essentially invented in the 1600s. And very shortly after this, in Dutch markets, people began certain other financial inventions like shorting. So they invented things like shorting. People have invented things like options, various other financial products that are quite interesting. But that's not what I want to talk about today. What I want to talk about is sort of how do we turn a voting machine into a weighing machine? And also, how would we do this if we wanted to avoid sort of perverse behavior like shorting? So I want to understand sort of the theory of long-only investing. And there are other financial inventions such as, money, debt, and other types of things. So what is it that I want to say about that? So, and then, so what does a stock do? So what is a stock fundamentally? So a stock is a company wants to raise money. So they sell little horcruxes of themselves to then make the decision that they to sort of fund their existence. So they sort of make these, they split apart their sort of entity into a bunch of things called shares. They sell these to people. And ostensibly that means you own some percent of the company. This isn't entirely true because people like the people who say a company owes debt to have prior claims. So it's a little bit complicated there. And there have been interesting sort of, banking type products invented over the years. If you look into something like Islamic banking, it's very interesting. There's sort of 5 to 7 contracts that sort of emulate other sorts of credit systems. So the way that credit systems are implemented are sort of often sort of look very different, but are sort of similar. Anyway, so now getting away from markets, we can talk about fuzzy allocation problems. So let's say that I want to go harvest these little like black truffles here. I don't know exactly how many of them are at each sort of zone that I might want to search. And I want to figure out how should I best spend my time on different zones. And the question is, in this example, we sort of see that you might not want to go to this tree because it doesn't look like it's productive. So we might not invest our time in all possible things. And this gets to a little bit of other theories of investment, such as, we look at people like Warren Buffett, where they sort of want to look at things that obviously are a good idea. He might only pick these two because he sees this as sort of poor and this is just no sign of truffles at all. And so actually looking at the environment is helpful, and you sort of choose a process of you choose your stuff via a process of exclusion. You get rid of the stuff that's obviously a bad idea, and you want to keep the things that are a good idea. That's at least the theory. Okay, so modern portfolio theory. So a geometric Brownian motion is something that satisfies this differential equation. So we want the logarithmic derivative to be some constant average rate of growth plus some variance times a Brownian motion term. And at time t, we see that s is supposed to be equal to, well, it's going to be the average minus this variance over 2 times t in the median, plus some error term which comes from the Brownian motion. So what that means, though, is that if we're trying to optimize for median growth, we need to optimize m minus the variance over 2 over all possible portfolios. And we likely prefer, say, conservative estimates on those maxima, and we want to overestimate things like the variance because we don't want to be wrong. Okay, so the penalty for this sigma being large can be quite painful. Okay, and if you can believe it, I was originally planning to give this talk on the board, but essentially this looks like, what the typical stock market chart looks like, something that's sort of like an exponential curve with some Brownian noise to it. Okay, so now we get to the second part of the talk. So I want to talk about, so we've introduced 2 different concepts. We've talked a little bit about mazes. We've talked a little bit about modern portfolio theory. So what I want to talk about is the right way to sort of think about a lot of allocation problems, or at least a way to think about a lot of allocation problems. So we have an inner product. So if I have a vector space H, I can have an inner product as something where, okay, so if I have the inner product of x with x, it better be positive. If the inner product of x with itself is 0, then I want x to be 0. I want it to be symmetric, and I want it to distribute over, addition and scalar multiplication. So the way that you can think about this is if you ever encountered something like the dot product in 3 dimensions, this is supposed to be some generalization of spaces that have a dot product. And essentially, these are exactly the spaces that have Pythagorean geometry in some sense, or Euclidean geometry. So we call this little double bar around x the norm of x. We're trying to give elements inside of our space a size. We want it to be the case that if I have an absolutely convergent sequence, it better converge to another thing inside of this Hilbert space. So this is what a Hilbert space is. A Hilbert space adds in this extra convergence property, which gives us some extra access to topology type arguments. Okay, so some examples of Hilbert spaces. Well, I could take classical Euclidean space where I have n coordinates for my point x, n coordinates for my point y, and I just sum up the coordinates multiplied together term by term. Okay, slightly maybe more interesting is if I have x and y random variables with finite variance on some base, I could talk about their covariance is exactly an inner product. If I have a positive semi-definite matrix where I can define this inner product, which is a little funny. If I have, so I can take the infinite dimensional generalization of Euclidean space. So I could take the set of sequences such that just infinite sequences where I define their inner product to be, just term by term multiplication. And the point here is that we really need that for this inner product to make sense, we really need that the x's are square summable. So x1 squared plus x2 squared is summable, which really just means that if I take the inner product of x with x, I should get out some finite number. Okay, and the set of functions on the unit interval such that whenever I take their integral, their squared integral, that's less than infinity. I can also view that as a inner product space, and that's where classical Fourier analysis happens, where elementary classical Fourier analysis on an interval happens. Okay, so let's sort of take these axioms for an inner product for a Hilbert space for a spin and prove the Pythagorean theorem. So we're going to define perpendicularity to be saying that their inner product is 0. Okay. And the point is that x is orthogonal to y if and only if the norm of x squared plus the norm of y squared equals to x plus y squared. Normally, you see that if x is orthogonal to y, then we have this relation for these three vectors. And the proof is just, okay, so I take the norm of x squared, the norm of y squared. That's really x hitting x plus y hitting y. But because this is assumed to be 0, I can just add this extra term in. And so then I get the norm of x plus y squared. And the point here being that this also notion of perpendicularity is very similar to, it's essentially the same notion of statistical independence when we have finite variance. And something that might be useful to you sometime in your life is that a 3, 4, 5 triangle must give a right angle. And this has been known for a very, very long time and is useful in construction. So if you want to build a right angle, you just need to have some triangle that has a unit 3 side length, a unit 4 side length, and then a unit 5 side length. The only way that those can line up is as a right triangle. So the fact that the converse of the Pythagorean theorem is true is at least has sort of been useful for quite a bit of time. And actually, that may be sort of the more classical way that people thought about it. So about Hilbert spaces. So the key, what we're going to deal with Hilbert spaces is there's this beautiful theorem called the Riesz representation theorem. It says that if I've got my vector space H, which is a Hilbert space, so it has that inner product, and I have a map that takes my Hilbert space into the reals, that's bounded and linear. So that says that if I take lambda of some vector x, that better be less than or equal to some uniform constant times the norm of x. Then there exists some actual point inside of my space that implements this linear functional. So we have this wonderful sort of self-comprehension of Hilbert spaces. So Hilbert spaces know about their linear functionals. They embed their dual into them, by which I mean if I have a linear map, bounded linear maps are all of the form x inner product with something else. And the beauty of this is that if I have so let's say that I have a space of functions on some set omega. So I have a bunch of functions on some set omega that form a vector space because I can add them and scalar multiply them and all that jazz. Such that point evaluation is a bounded linear function. So I want to have something so that whenever I evaluate these functions, the map taking my function to its value at x is a bounded linear function. And so then that says that as kernel, this means that there have to be these special elements of our Hilbert space called kernel functions. Because, okay, I had lambda of x hitting f was f of x. So that means that because this is a bounded linear functional, there has to be some vector kx such that whenever I take f hitting kx, I actually get f of x. And so this allows us to self-comprehend function values. So the, 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 But we also saw in, well, I'll talk about it in a minute. So some examples of reproducing kernel Hilbert spaces, we could have Euclidean space where we view vectors as functions on 1 up to n. I think in a more modern data science type setup, if you're writing software, you often won't index your columns by numbers, but we could also view it as functions on certain, labels. Up to relabeling by the numbers, which is, sometimes easier said than done. Little L2, so the sort of square summable sequences form one. Not big L2, so not, because the point is that having this integral be defined really only requires that the function is defined almost everywhere. So something sort of goes a little haywire there. And the final one that I want to talk about is the space of harmonic functions on the unit disk, such that their coefficients are square summable. So it's going to have some series, Cn times z to the n. And so harmonic functions are all of this form. But harmonic functions of this form, such that we have their coefficients summing to less than infinity. Then I can define this kernel function kw of z as this, and this is called the real Hardy space. So this is a very convenient to deal with kernel that's been very well studied. It's not well, it's even more well studied without this real part, but it's sort of an example that we're going to use a little later. Okay, was there a question? Sorry. No. Okay, so there's some wonderful tricks that you can do with kernels that have sort of become more important in recent history. So if I have a function with a Taylor series and its Taylor coefficients are positive, then if I have a kernel such that it makes sense to evaluate f of that kernel, that f of that kernel is still a kernel. So this is sort of nice. So for example, we see like exponential type kernels. These are sort of Fox-based type kernels. There's these other sort of Jury-Arbison type kernels. And this one would require your kernel function to be bounded above by 1 for it to be sort of in the domain of convergence of this function. So one thing that's nice is what happens whenever I take these transforms going from a kernel to some new kernel. Well, kernels, if we're on, say, a compact set, we can write them as a sum of squares like this. So fi of z times fi of w. It might be an infinite sum, but it will converge. And so then if I took 1 over 1 minus the kernel, and I just sort of distribute out what this is, I get all possible arrangements of multiplying the f's together. So what this says is that I took a space that had, say, linear type functions, and then I added a whole sort of function algebra over it. So this is something that's very nice. This is what happens whenever you go from one kernel to these more complicated kernels. So then we can deal with, say, more functions, and this sort of emulates having a feature map. Okay. And the nice thing in this kernel is actually that sort of it has multipliers, which is rare for exponential type kernels. But I'm not going to talk about that today. But the theory of multipliers of reproducing kernel Hilbert spaces is quite interesting. So there's the kernel embedding trick. So if I have a reproducing kernel Hilbert space H, well, okay, so we said that I could sort of, for each point, I have some point evaluation functionals. So then what I can do is I can take convex combinations of those to get a to get essentially things that correspond to a measure supported at, say, finitely many points. And in general, if I have a probability distribution on my space omega, I can write these kinds of integrals against these kind of expectations of these functions as f inner product with some element of the Hilbert space. So somehow I can correspond measures or probability distributions with elements of my Hilbert space. And the point is that, okay, we've heard a little bit about, and so here if I had finitely many point masses, so I had a mass at n little points, then the point is that I could have f hitting this new is just going to add up the functions at those points according to those weights. So, so this is sort of a very so this is very nice because we have a way to turn distributions into elements of a Hilbert space. We heard a little bit in previous talks, both in the first week and some I think this week, about things like Wasserstein distances. So if I need to take a pile of dirt and move it to some other location, I could have a dump truck style moving distance, which is given by the Wasserstein distance. But the point is that these sorts of Hilbert space embeddings give some relaxation of that. So they give a distance between distributions that's often fairly easy to calculate, because Hilbert spaces are like Euclidean space, and that's like a very familiar set. Okay, so I'm going to have the set of distributions be exactly just this set MK. So, okay, and there's been a recent set of applications to dynamics that I'm not going to talk too much about. So if I have a function from my set omega to my set omega, then we have these things called parent-Frobenius operators, which, okay, this should be a capital F. So I want to have the parent-Frobenius operator. When I apply a kernel function to it, I should get back the kernel function at a different point, which is the kernel function at f of x. This should be a capital F. I'm sorry about that. And finding mu such that this parent-Frobenius operator hitting mu equals to mu is somehow corresponding to finding orbits. And this is the general philosophy of Koopmanism, which is sort of allows you to sort of universally model a lot of dynamical systems, and seems very similar to things that are going on in learning literature. But that's okay. So now I want to talk about so let's say that I have a continuous function on my space omega. Let's say that I want to find the distribution that best approximates it. Overall possible distribution supported on some compact set K. Then formally, okay, if I expand out this inner product, or well, I expand out this norm, okay, the norms were, let's see what we did before. See here, we had this expansion here and expanded out to this. Well, if I change the plus to a minus sign, I get exactly this. So this has a minus sign. Okay, so, but the point is that, okay, this norm of psi squared is constant, so I can turn it into something that we're going to call the aesthetic objective, which is, okay, so if I have a distribution mu, I'm going to give it a score, which is, okay, it's going to be the integral of psi d mu minus this norm of mu squared over 2. So sort of this is we should typically think about this as an expectation term. So like this is, say, an expected return, and this is some energy penalty for how risky everything was. Okay, and it's all meant to align with that geometric Brownian motion model from earlier.
James, can I answer a question?
Oh yeah, please.
Just make sure that I understood it correctly. You're thinking of omega as like different company valuations, and mu as the underlying portfolio that's the best performing, but you don't know what it is, and phi as different portfolios that you're optimizing over?
Yeah, so I want to optimize over. Can you repeat the question? Sorry, I couldn't hear you very well.
I guess I was just wondering, like, what is omega and phi and...
Okay, so omega we should view as a space of states. It could be the space of stocks, but we want to view it as sort of its, yes, so we could view it as like a space of stocks. We could view it as some subset of Rn. We can view it as, it's supposed to be just a general sort of space that we would want to live in. So our space of data. So omega is supposed to be our space of like data, which we have some correlation type relationships with. So the way that I typically think about it is we have access to a bunch of random variables, and we know sort of their sort of omega, the points of omega are, say, the different random variables, which in the case of, say, portfolio allocation is, say, the stocks. Does that seem okay?
Sorry, what's the dimension and what's a typical element in this case?
Okay, so one thing that's nice here is that oftentimes it could be some very low dimensional manifold, but it's like, I mean, if we're talking about whenever we do the kernel embedding, it could look very low dimensional if in practice. But omega could be infinite dimensional. It doesn't need to be even realized as a space subset of Rn. It could be just some general space. Yeah. And the nice thing about this is that the reproducing kernel Hilbert space on, so let's go back to here. So the reproducing kernel Hilbert space on a set can often be infinite dimensional, even though the manifold that it's on is say finite dimensional. So for example, here we have the complex unit disk, but if I look at the reproducing kernel Hilbert space, actually, so the complex unit disk is two-dimensional, and this kernel is somehow, these kernels actually are going to span an infinite dimensional space because the space of harmonic functions is infinite dimensional. So that's sort of, yeah, so sort of the kernel embedding actually lets us get more dimensions for free as well. It's sort of a bonus. Okay. So the nice thing about this objective formulation is that this psi doesn't actually need to be in the Hilbert space. So we could be trying to approximate something that doesn't exist. Like, and this especially sort of makes sense for things like, at least it makes sense to me for like portfolio theory, is the case that this might not be like something that's actually possible. But so then, but you still do find a maximizer here. Okay. And so I'm going to call the embedded maximizer the topiary of K with respect to psi. So just because of this connection to hedging that we saw earlier, where we had these two coin flips, essentially, if we were to take the distribution on that two coin game, we would want to spend half our money on one coin and half our money on the other coin just by symmetry. Okay, so in the economic context, we have psi being this function giving expected returns over all assets. So this could really be a finite sum. And this is somehow the variance of that portfolio. So the inner product being given by covariance. And so if we try to do this on long, and this is the version on long-only portfolios where we're only positively investing, because that's what I required. It required them to be probability distributions. So that means I'm not shorting anything or selling anything that I don't have. And in practice, direct application gives extremely sparse portfolios. So if I analyze like 1,000 securities, it might give me an optimal portfolio based on only a few dozen assets. And so this causes a lot of controversy around modern portfolio theory because it's fundamentally underdiversified. But what's even more interesting, and so, you know, a lot of that could be from the case that like, okay, last month's performance may not be a very good indication of this month's performance. You know, things about the business environment can change. But even if we start removing things like what that appear to be outliers, we still get this sparsity phenomena. And it's something to do with reproducing kernel Hilbert spaces, which we'll talk about in a minute. There's also another strange thing that we're not going to talk about today. But if I have a bunch of assets with apparently the same return, and I take the minimum variance portfolio, it does even better than that I could assemble from those assets that have, say, about equal return. It actually often does better than this would predict, which is something called the low variance anomaly. So low variance is somehow even better than it appears to be. So this sort of stability. Okay, so if I differentiate this objective function, I happen to get some sort of marginal. We don't really need to know what it is, but it's a function that has some formula. And if we have something that's our optimizer, then it needs to be, the marginal needs to be non-positive at every point. So that's sort of the point, is that this marginal has to be non-positive because, okay, if I wanted to do gradient descent in some direction, let's say adding a little more allocation at some point x, I would want this derivative to be positive, whatever it happens to be. And so if I'm at an optimizer, it better be the case that the derivative with respect to everything else is either negative or zero. And the set of things where it's actually zero have to be, if you think about it for a few minutes, those have to be exactly the constituents of your optimal portfolio. So the point is that the things that are in your optimal portfolio, you're going to want to buy. You're going to want to buy and say like your marginal incentive to buy one of them and your marginal incentive to sell the other should be zero. So the point is that it should be the case that they're sort of perfect substitutes infinitesimally. It's calculus, I guess. So, and so we're going to call something an index if actually I would use all the assets if I bought it. So let's say that we believed that the S&P was some coherent group of 500 companies. I would call it a topiaric index if really whenever I ran this optimal portfolio algorithm, I got all 500 companies, which isn't going to happen in practice, but that's what I'm going to call an index here. And what I want to talk about is how these break and how they lose coherence pretty rapidly. So we have this marginal, but the key is that there's also this, so if we talk about harmonic functions, those are supposed to be the steady states of things like heat distributions. So a way to think about harmonic functions is as the steady states of heat distributions. And so if I had a point in the middle of like a hot plate that I had, and it was hot at the middle, that heat would have to diffuse. So I couldn't have been in a steady state. So this means that the maximum for heat distributions needs to occur on the boundary. And similar phenomena occur in complex variables and over general functions, which is quantified as the Sheloff boundary. Okay, and then, well, okay, there's a maximum principle for kernel embeddings, which we're going to call the green frontier. So you can define it. It's some complicated thing, but it's exactly the set of generic maximizers. And what we say is that the best possible portfolio making stuff out of general, say, points from omega is the same as taking it from this green frontier. So we can choose from only sort of some sort of distinguished boundary, which we'll see in a minute. We'll see some pictures in a minute. There's also sort of pricing inequalities. The main thing here is that this is sort of very similar to sort of geometric function theory type inequalities, but I don't want to talk about that today. But the point is that we do get some geometry near the boundary of, and certainly near the points that are going to be inside of our optimal portfolio as to the functions in our reproducing kernel Hilbert space, which sort of is very similar to what are called like Julia type inequalities in complex analysis. So the point is that there's a lot of geometry from things like complex analysis that sort of replicates itself in reproducing kernel Hilbert spaces, and we can get certain kinds of functional inequalities just on certain values involving things that are sort of analogous to the things finance people care about, like beta and alpha and that kind of stuff. But that's not so important for today. So what I want to talk about is we have this thing that said that I mentioned earlier that there's the theory that a optimal portfolio is a broadly supported index fund weighted according to the real economy, like, for example, Vanguard or these Bogleheads type people. Whereas you have people like Warren Buffett who think, no, I should pick some really small set of things and really investigate them. But what's interesting is this is sort of related to a salience issue. So if I have a set that's contained inside something that is an index, if I try to take the optimal portfolio from that smaller set of assets, then I'm going to actually get something that best approximates the variances of this optimal portfolio that exists for this topiaric index. So imagine the S&P as an index, and it has 500 stocks in it, and I would actually be able to buy those with all positive allocations if I ran this algorithm. Then let's say that I only knew about 50 of those stocks because I don't pay that much attention to Wall Street. I might get some very small portfolio, but somehow its variance will be the best approximation of the variance of this index that I'm contained in. So I'll be best matching the behavior of this coherent outfit. One way you can think about these kinds of like topiaric indices is that you can think about them a little bit as like assembling an outfit. So if I have a red hat and it doesn't go with my outfit, then I can't wear the red hat. So somehow this is why stocks get left out, is that somehow there's nothing actually canceling them in the environment. So our salience is very important here. Okay, so then one other thing that's sort of nice is, okay, so if I have a topiaric index, I can remove one thing from it and get another topiaric index, and then remove another thing and get another topiaric index, going all through the portfolio. So I can actually linearly order it, which was sort of surprising to me. I don't have any real applications for this, but somehow this is sort of mildly interesting, that sort of an outfit of things makes sense even whenever you take off one thing at a time, but you have to do it in a very particular order. And if you want to sort of run sort of numerical type stuff, you get, in the worst case, you'll get some sort of like law of large numbers type convergence. But, okay, so now, okay, so, I know I'm tasked with getting you to lunch on time, so we're going to finish things up. You'll notice the slide counter, they're going to start to go really, really fast soon. So back to physical maze solvers. Okay, so we have this cheese outside of the maze. The smell lines go into the maze. The orange dot follows the smell lines out and gets the cheese. So it knows how to find the way out. And there's various sorts of riffs on this that are, that are more similar and less similar, such as we've seen talks about slime mold solving mazes. And they're not exactly quite the same, but they do sort of use similar type ideas. So what I want to talk about now is about sort of maze solving. So first I'm going to leave this slide up for a minute. So if we use the space of harmonic functions, and we have a maze inside of the disk. So for example, this little brown curve inside of the disk, these pair of brown curves inside of the disk that don't contain 0. Okay, then if I start out at 0, well, the maximum principle says, or the minimum principle for harmonic function says that the minimum is going to occur, say, on the boundary. So if I start out less than the value, so what this is supposed to be here, well, I'll tell you this in a minute. So if I graph my aesthetic margin for the optimizer here, we see a few things. So if I were to start out at 0, this is the aesthetic margin. So I've got where it's greater than 0 and where it's less than 0. So the black part is sort of where the aesthetic margin is less than 0, greater than 0, and this is where it's less than 0. So if I start out here and I want to navigate my way out, I just follow the contours of the underlying harmonic function, because I can move through this black region because we know the function is, say, big on this yellow region or something like that. And the interesting thing also is that, so if these red things are the stocks that we're going to have inside of our optimal portfolio, sort of taken from this artificial harmonic function setup, we see that where they hit this marginal is sort of their tangent here. So I want to sort of talk about how we got to that, and then I'll finish up, maybe a little early. But okay, so what do I do? So first I pick something to buy, and I might buy something else, and then I'm going to get these kinds of marginals. I keep doing that. And eventually I get to the point where whenever I wanted to buy something, so the next thing that I wanted to buy is supposed to be up here, I had to remove this one. So that sort of means that my outfit didn't make sense anymore, so I had to take off my hat. And then we sort of continue, and it adds and subtracts stuff, sort of thinking about which things are sort of the best. And then we get out some, we eventually converge to some function, and it's supported at about 4 points. Really, it might be 5 or 6, which is sort of nice. So it's sort of fun to watch on bigger examples, but we can do it on this example here, just because the convergence doesn't take a million slides. Okay, so now in the harmonic function case, there's a trichotomy here. So if my maze actually doesn't connect to the outside, and this is my origin point, then I'm going to buy actually sort of almost everything along this boundary. And this sort of corresponds to something like the Cauchy integral formula. And if I actually contain the point 0, I'm just going to buy that single point. So that's sort of like, so here we sort of see this broadly diversified case where we actually surround this point. And here we see, well, okay, we just bought the index fund. We bought one thing because that the point mass at 0 was really the best here. But here, it's sort of interesting. In these intermediate cases where you actually can escape, it necessarily has to be finite. So the support of these things has to be finite. And the fact that we have finite support in this harmonic function case sort of relates to the fact that sort of if I had a accumulation of zeros along this boundary, it sort of have to be 0 along this whole boundary. And then we could argue that the function had to be 0 or something, or constant, which isn't going to be the case because you can't figure out the value of a function here from the values of the function on here for reasons to do with Runge's theorem. So what I really meant to do with this talk, especially with a couple of things, but there's something that I talked about just for a short minute. So this Koopmanism is a still river that runs pretty deep, and it's been quite successful in understanding dynamics recently, and may be useful to understand things like recurrent neural networks. And so there's a Hilbert space problem book. That's basically like a puzzle book. It's by Halmos. An Introduction to the Theory of Reproducing Kernel Hilbert Spaces by Paulson and Raghupathy is just a beautiful work, and it's significantly shorter and sort of can give you some quick and dirty stuff about sort of nice extra geometric features of reproducing kernels. And there's also a nice sequence of talks by Schiller about financial markets. So now that we've talked a little bit about embeddings, we also saw these in a variety of other contexts. So I wanted to close with just a few comments on the fact that we can do things in a much broader, but we do things in a much broader context. So whenever we saw Jacob's talk, for example, we saw word embeddings. And we saw that somehow if you had the average of the word embeddings of the words in a sentence, somehow that was coherent in some way. So one way to sort of formalize that is sort of that those vectors maybe need to point in similar directions or they need to move around in some kind of way. Not sure exactly what did there, but the point is that this geometry of reproducing kernel Hilbert spaces, this ability to constructively build long vectors or short vectors and optimize different kinds of and sort of understand like a way to turn your data into vectors that then you can add up and talk about their geometry is very, very powerful. And I would highly recommend if you do get your hands on this book, it's wonderful for learning a lot more of the theory than ends up getting applied. My real question about a lot of this stuff is that I think that in the long term, understanding more novel things about reproducing kernel Hilbert spaces could be useful in a lot of different things. Like, but I'd like to thank you for your time. Thank you for being patient with me. I'm pretty sick. I got a pretty high fever. I intended to give this talk on the board, so sorry if there were a couple of typos, but thank you so much for your attention.